conservation of energy, and non-conservative forces. In the video Principle of Conservation of Mechanical Energy, we saw that if only conservative forces act on a system, the mechanical energy of the system remains constant. In our attempt to understand and describe the universe, where things change continuously, conserved quantities are of great help. Unlike Newtonian dynamics, which requires knowing the details of the motion in order to solve a problem, using energy places us in front of a new approach. With its application, we can determine the final state of a system from an initial configuration without paying attention to the intermediate stages it goes through. Generally, the quantities are conserved under special conditions. Thus, the forces found in nature can be divided into two categories: conservative and non-conservative. We had defined a conservative force in two ways. A force is conservative if the work it does on a particle moving between any 2 points, whether done by it or against it, is independent of the path, as we can see in the diagram. The mass m, following different paths, always does the same work to move from the floor to the table, the product of mg and the height. This means that the work done by the force depends only on the initial and final positions of the body. The second definition states that a force is conservative when the work done by it along a closed path is zero. Thus, the work required to move the mass m from point A, B, is equal to the product of the force we apply against the weight, which acts in the same direction and sends the displacement h. Therefore, the cosine between the two vector magnitudes is the cosine of 0 degrees. And the product will be m per h. But the work from B to A would be equal to the product of the weight md times the displacement. However, the displacement has an opposite direction. Therefore, the angle formed between them is 18 ode y, and the cosine of 180 degrees is -1. So, the work will be the same as the previous one but with the opposite sign. If we sum both works, the total work done from A to B or the starting point along a closed path will equal 0. Confirming another way to define a conservative force. In general, a conservative force is a function of position only and not of velocity or time. The force from A to B is conservative because it depends only on the initial and final positions of the particle. Similarly, the elastic restoring force, shown in red, is conservative because the work done by a spring depends only on its initial and final deformation states. But what happens if non-conservative forces also act? For example, friction or viscous drag forces. By the work energy theorem, we know that the work is equal to the change in kinetic energy. Here, the equality appears Q, the work of conservative forces plus the work of non-conservative forces. From the work energy potential theorem, we know that the work done by conservative forces is equal to the negative change in potential energy. Substituting this into the expression, we obtain this equality. By grouping the changes in kinetic and potential energy on the second side of the equation, it shows that the work done by non-conservative forces is equal to the sum of the change in kinetic energy plus the change in potential energy. This leads to the conclusion that when non-conservative forces do work, it equals the change in the mechanical energy of the body system. In other words, mechanical energy is not conserved when non-conservative forces are acting. Next, as an application of what has been discussed, we will solve the following example. What does it say? A 2K block slides along a horizontal surface with a coefficient of kinetic friction, Bk point through Mach 1.30 B030. The block has a speed of 1.3 meters per second when it collides head-on with a massless spring. If the spring has a spring constant K120, 100 and K20 N per meter, first question QA, how much will the spring be compressed? Second question NBG, what will be the speed of the block when it separates from the uncompressed spring? As shown in the diagram, the initial situation is when the block are moving at 1.3 meters per second, starts compressing the spring, and the final situation is when the block comes to a stop. Now, comparing the energies. In the initial situation, the elastic potential energy is zero, but the kinetic energy is not. It is the kinetic energy the block has as it comes in, that is, half the mass of the block times its initial velocity squared. The work done due to friction between the block and the surface is equal to the coefficient of kinetic friction times the normal force. That would be the frictional force, which opposes the displacement, hence the negative sign in this expression. The displacement we have chosen to denote as delta x. This is what appears on the first side of the equation. On the second side, as we anticipated, the final kinetic energy is zero because the block comes to a stop. However, it reaches the maximum compression, having elastic potential energy, which is half of the spring constant K times the displacement, ton x dot delta x dex squared. In this expression, after substituting the values, which are given in the problem, and then grouping them together, we obtain this final equation, which, as we can see, is a quadratic equation. The equation will have two solutions. One is valid, which is 0.31 meters, and this is how much the spring will compress. The other solution, which we do not include, is 0.2 meters, which would not be consistent with the analysis of the displacements we have done. Therefore, we discard it. The block will end up in this situation once the spring's compression is complete. In part B, we need to analyze the situation when the block separates from the spring once it has decompressed. In other words, it returns to its initial position. This is when the spring recovers its original shape. Now, the initial situation is as follows. The initial elastic potential energy, which we know, is half of the spring constant K times the displacement delta x squared. The kinetic energy in that situation is zero, because the block is at rest. The work done, the non-conservative forces, will be equal to the frictional force multiplied by the displacement, which already has a known value of 0.14 meters. On the right-hand side of the equation, only the final kinetic energy will appear at the end. The kinetic energy with the final velocity. This is when the spring ejects the block, and not the elastic potential energy, because at that point the spring has recovered its original shape, and the block no longer gains elastic potential energy. Substituting the known values, we are left with solving for the final velocity, which will be 0.5 meters per second.